Hello and welcome. Today, we're going to take a journey to a place so small it's almost impossible to imagine, so we can really understand the building blocks of, well, everything. We are going to decode the structure of the atom. And it all kicks off with a pretty simple question. You've seen a fireworks show, right? You've seen those incredible, vibrant colors, a stunning crimson red or a brilliant green. Have you ever wondered how they do that? Why isn't it just a generic orange flame? It looks like magic for sure, but it is pure science. You see, the answer to that mystery is actually a secret message, a code that's being broadcast from the very heart of matter itself. And today, we're going to learn how to read it. Our whole mission is to crack the code that atoms use to talk to us. So here's our game plan. We'll start with that colorful atomic mystery. Then, we'll need to understand the messenger, light itself. From there, we'll check out a brilliant but ultimately flawed early model of the atom, see exactly where it started to fall apart, and then dive into the wonderfully weird quantum model we use today, which gives every single electron its own unique address.
Okay, so let's start with clue number 1, those colors. It turns out when you heat up different elements, they don't all just glow orange like a piece of hot metal. Nope, they glow with their own special signature colors. And what's so wild is just how specific these colors are. If you put some cupric chloride in a flame, boom, you get this brilliant green. Use strontium chloride instead, and you get that deep crimson red we love in fireworks. You know that kind of yellowish orange glow from a lot of old street lamps? That is the signature color of sodium. Every element is sending out its own unique message using colored light. And this leads us to a really crucial idea. Scientists figured out that these colors aren't just a solid smear of light. If you look closely, they're made up of very specific, very sharp lines of color. We call this a line spectrum. And it's so unique to each element, it's basically an atomic fingerprint. We can figure out what elements are in a distant star, millions of light years away, just by reading its light. It's amazing. All right, so atoms are sending us messages using colored lights. That's cool. But to really understand the message, we have to understand the messenger. So what is light really? And how in the world does it carry all this information? Well, at its most basic level, light is an electromagnetic wave. You can picture it like a ripple moving across a pond. It's got a wavelength, that's the distance from the top of one wave to the next, and a frequency, which is just how many waves pass by a certain point every second. And these two things are always connected. Long wavelength, low frequency. Short wavelength, high frequency. Every single color you can see just corresponds to a very specific wavelength of light. Now, for centuries, scientists assumed energy was continuous, like a ramp. You could have any amount of it you wanted. But then, in the early 1900s, a guy named Max Planck completely changed the game. He came up with this revolutionary idea that energy isn't a ramp at all. It's a staircase. It can only be gained or lost in these tiny specific packets, which he called quanta. And here's the kicker. The energy of one of those packets is directly tied to the frequency of the light. That's the big takeaway here. High-frequency light, like blue or violet, is made of bigger energy packets than low-frequency light, like red. The exact size of these energy steps is determined by a fundamental constant of our universe, something we now call Planck's constant. We just call it h. It's a ridiculously tiny number, which is why we don't notice this whole staircase effect in our day-to-day lives. But when you get down to the scale of an atom, it is the single most important rule there is. So now we have two huge clues, right? 1, atoms have unique color fingerprints, and 2, light energy comes in these specific packets, these quanta. The first person to really connect these dots was the Danish physicist Niels Bohr. Bohr's big idea was to picture the atom as a tiny little solar system. He suggested that electrons couldn't just hang out wherever they wanted. They had to be in specific, fixed orbits around the nucleus, kind of like planets orbiting the sun. Each one of these orbits corresponded to a very specific, allowed energy level. An electron could be on one step of that energy staircase or the next one up, but it could never be in between. And this explained the color mystery so elegantly. It works like this. An electron is normally just chilling in its lowest possible energy level, what we call its ground state. Now, if it absorbs the exact right amount of energy, a specific quantum, it can literally leap up to a higher orbit, an excited state. But this new position is unstable, so the electron quickly falls back down to where it started. And as it falls, it has to release that extra energy, which it does as a single packet of light, a photon, with a very specific frequency and therefore a very specific color.
For the simplest atom out there, hydrogen, this model was a huge home run. It predicted the exact colors, the exact spectral lines that hydrogen gives off. The energy difference between those fixed electron jumps perfectly matched the energy of the light quanta in hydrogen's spectrum. For a minute there, it really looked like the case was closed. The code was cracked. But science never really stops, does it? Just as everyone was celebrating Bohr's beautiful, simple solution, new evidence started to show some pretty serious cracks in this whole planetary picture. Yeah, there were some big problems. First, when scientists got better tools and looked super closely at those spectral lines, they saw they were actually made of several, even finer lines all clustered together. Bohr's model had no explanation for that. Second, and this was the real deal breaker, the model only worked for hydrogen. It totally failed to predict the spectra for any atom with more than one electron. And finally, it never actually explained why. Why were electrons stuck in these specific orbits? It was just a rule with no real reason behind it. This basically forced scientists to ask a mind-bending question. This whole neat and tidy idea of an orbit, like a little racetrack for the electron, what if it was just plain wrong? What if electrons don't have predictable paths at all? And that very question blew the doors open to the modern quantum mechanical model of the atom. This new way of thinking tossed out the idea of fixed paths and instead welcomed us to the truly weird world of quantum probability. Okay, let's make this super clear, because this is a massive change in thinking. Bohr's orbit was a flat, 2D path where you knew exactly where the electron was supposed to be. The modern orbital is something else entirely. It's a three-dimensional region of space, like a cloud of probability that only tells you where you are most likely to find the electron at any given moment. It's not a path, it's a weather forecast for an electron. So why the switch to probability? It all comes down to the famous uncertainty principle. The deal is, at this tiny quantum scale, the very act of measuring an electron's exact position would mean hitting it with so much energy that you'd totally change its speed. And trying to measure its speed would mess up its position. You literally cannot know both perfectly at the same time. So the best we can possibly do is define a region where it probably is. Okay, so if electrons are just living in these fuzzy clouds of probability, how do we describe them with any precision at all? Well, the answer is this really beautiful mathematical system called quantum numbers. You can think of it as a complete, unique address for every single electron in an atom. This address has 4 parts, 4 quantum numbers that, together, tell you everything about an electron's state. First, you have the principal number, n. Think of that as the city and zip code. It tells you the main energy level, or shell, basically how big the orbital is and its general energy. Next, the angular momentum number, L. That's like the street name. It actually defines the 3D shape of that orbital. Is it a simple sphere, a dumbbell shape, something more complex? Then you have the magnetic number, M sub L. That's the house number. It tells you how that specific shape is oriented in space. And finally, the spin number, M sub S. This describes a property of the electron itself, sort of like it's spinning on its axis. It can only be one of 2 ways, which we call spin up or spin down. And atoms are very particular about how they fill these addresses. They follow 3 main rules. First is the off-bow principle, which just says that electrons are kind of lazy. They always fill the lowest energy spots available first. Second, the Pauli exclusion principle. This is like a cosmic no 2 people at the same address rule. It says that no 2 electrons in the same atom can have the exact same 4 quantum numbers. This means if you have 2 electrons in the same orbital, they have to have opposite spins. And last, there's Hund's rule, which is sort of the personal space rule. When you've got orbitals of the same energy, electrons will go into separate orbitals first before they ever start to pair up. So there you have it. We went from a simple firework color all the way to a complete 4-part address for every electron in the universe. We've decoded the message of the atom. So now that you know the rules of the game, I'll leave you with a challenge to chew on. Using these principles, what would be the complete 4-number quantum address for the very last electron in a chlorine atom? Give it some thought. Thanks for joining me on this one.